In this video, we will be looking at section 3.4, which is based on moments and moment generating function of a discrete random variable. By the end of this video, you should be able to define, derive, and calculate moments about zero, moments about the mean, first moment about zero for a given PMF, and calculate the second moment about the mean for a given PMF, as well as calculate the third moment about the mean for a given PMF and calculate a measure of skewness. So what are moments and what is a moment generating function? In statistics, a moment refers to any quantitative measure that tells us about the shape of the probability distribution. So if it tells us where the distribution is centered, where the mean is, if it tells us about the shape of the probability distribution, whether it's symmetrical or if it's negatively skewed or positively skewed, then those measures are called moments. Then a moment generating function is a function or a formula that calculates or generates these moments. And all moments are expected values, either expected value of a random variable x or the expected value of a function of a random variable x. So if we have expected value of a random variable x or a function of a random variable x, then we call that numerical value or measure a moment. Now, a moment generating function is the expected value of a function of random variable x, where this random variable x is equal to e to the power tx. Now, there are two types of moments. So we have raw or moments about the origin or zero, as well as central moments about mu. Right, so I'm just going to do a table here just to show the difference between raw or moments about zero, as well as central moments about mu. All right, so let us look at the first moment. So when we say the first moment about zero, we mean calculate the expected value of x minus 0. So it's about 0, and this is equal to the expected value of x, or otherwise known as mu. All right? Now, the second moment about 0, its expected value of x minus 0 all squared, and this is equal to the expected value of x squared. Now, the third moment about 0, its expected value of x minus 0, so it's about 0, all to the power 3, and this is the expected value of x to the power 3. The fourth moment about 0 is expected value of x minus 0 all to the power 4, and so that is the expected value of x to the power 4. Now, if I continue this pattern r number of times, then I'll say the rth moment about 0 is the expected value of x minus 0 all to the power r, and so that is the expected value of x to the power r. Okay, so that's how we define moments about 0. Now let us have a look at central moments about mu. So the first central moment about mu is defined as the expected value of x minus mu, and that is equal to the expected value of x minus mu, and that is equal to 0. Now, the second central moment about mu is defined as the expected value in brackets. You have x minus mu, so it's about mu, all squared, and so we know that this is equal to the variance of random variable x. Now the third central moment about mu is defined as the expected value of x minus mu all to the power 3. And then the fourth central moment about mu is defined as the expected value of x minus mu all to the power 4. And so if I continue the pattern, then the rth central moment about mu is defined as the expected value of x minus mu all to the power r. Do you see the pattern? So if it's about mu, then you subtract, if it's about 0, so you subtract there 0, so it's x minus 0 for the first moment. And then if it's about mu, then you subtract the mu. All right. And it will be clear which moment you need to define. So if you say define the second moment about 0, it means that it will be this one here, the expected value of x squared. So the expected value of x squared is the second moment about 0, while the variance or expected value of x minus mu squared, that is the second central moment about 0. So you have to say the word central because of the expected value or because of mu there. Mu tells us where the probability distribution is centered. All right, so I'm going to list then the important moments that you need to take note of. The first one, so it's the first moment about 0. So the first moment about 0, that is defined as expected value of x minus 0. That is expected value of x. In other words, that is mu. Now, mu tells us where the probability distribution is centered. So if you have a line graph with possible values 0, 1, 2, 3, 4, and 5, where we have their possible values 1, 2, 3, 4, and where the mean is equal to 3, then we see that the probability distribution of random variable x there is centered at the value 3, right? So mu tells you where the probability distribution is centered. Now the second important moment is called the second central moment about mu. Okay, so we're interested in this one. And this one, it's defined as expected value of x minus what? Mu, right? Because we said about mu, all squared. So this too is because we're looking at the second moment. And we know that this is the definition of the variance. And so we know that from the variance, we can get also the standard deviation. It's just the square root of the variance. And we know that the standard deviation and the variance tells us more about the spread and the dispersion within the probability distribution, right? So if we have, let's say, two line graphs where you have possible values for one example A there, and if we have here for B possible values there and there and there as well as there, we could see the dispersion or the spread amongst the possible values, right? And specifically, if let's say we have there for this specific line graph, suppose that we have the mean centered around this point here, then we could say that the points or the possible values of x are not too far away from the center, or not too far away from mu. All right, and then let's say for this example, this line graph, mu is a value somewhere around there. So that is where the probability distribution is centered. And so for this line graph, we could see that the possible values of random variable are actually a bit far away from mu, from the expected value. And so the standard deviation lets us know of the dispersion or the spread between the possible values and the expected value. So if your probability distribution looks like that, then it means that your possible values are closer to the expected value. All right, they're not too spread out. While if we have here a line graph or probability distribution that is curved like in that way, then it means that we have more dispersion, or the possible values a bit far away from the expected value. All right. And then the third important moment that you need to take note of, it's called the third central moment about mu. And so this is defined as expected value x minus mu, because it's about mu, all to the power 3, since we're looking at the third moment. And we're going to use this third moment to define a measure called skewness. So skewness is defined as, skewness of a random variable x, is defined as the expected value of x minus mu, all to the power 3 divided by sigma 3, where sigma is equal to the standard deviation of a random variable x. Alright, so if we have then the value of your moment, or the expected value, divided by your standard deviation to the power 3, then we would have defined then a measure called skewness. Now skewness lets us know if the probability distribution is symmetrical. So if it's symmetrical, then your line graph or the curve over your line graph will look almost like this, where the left hand side is equal to the right hand side, right? So if it's symmetrical, then the skewness of that random variable will be equal to 0. If it's negatively skewed, then your line graph, if you draw a curve over your line graph, then your curve will look something like that. So we'll say here that skewness, or the value of skewness, will be a negative 0. And so this will be negatively skewed, or skewed to the left. If it's positively skewed, then if you draw a curve over your line graph, then it should look something like that. And so we'll say here that skewness, it's positive or greater than 0, and your distribution is positively skewed. All right, and then the fourth moment that's important, it's the fourth central moment about mu, and we will use the fourth moment, a central moment about mu, to calculate something called skewness. Kurtosis. So we will use that to calculate kurtosis, where kurtosis tells us about the tails of your probability distribution. All right. So for some probability distributions, they have different shapes, right? So if we have a specific value for a kurtosis, then it would let us know about the shape of the tails, or how the tails look like. All right. So you either have distributions with heavy tails or longer tails, or with much shorter tails, right? But in section 3.4, you will be expected to calculate up until skewness. We will not ask you to calculate kurtosis. All right, then let us look at example 3.26, which says, suppose that the PMF of random variable x, which denotes the number of points earned on a short quiz, is given by this table here. So we see that random variable x has possible values 0, 1, 2, and 3. All right. Now let us define the first moment about 0. So what am I asking you to calculate here? So I'm asking you to calculate the first moment, all right, which is equal to the expected value of x. And by definition, this is equal to the sum of x times px for all possible values of x. This is equal to 0 times 0 0.1 plus 1 times 0 0.2 plus 2 times 0 0.3 plus 3 times 0 0.4. And the expected value there is equal to 2. Alright, now calculate then the second central moment about mu. Now what am I asking you to calculate here? I'm asking you to calculate the expected value of x minus mu squared. And so by definition, this is equal to the variance. Alright? And so the expected value of a function, we know that is equal to the sum over all possible values of x of that particular function times the probability. Now this is equal to the first possible value. We have 0 minus mu. What is mu equal to? In this case, mu is equal to the expected value. And so we have 0 minus 2 squared times 0 0.1 plus 1 minus 2 squared times 0 0.2 plus 2 minus 2 squared times 0 0.3 plus 3 minus 2 squared times 0 0.4. And so the variance here is equal to 1. And the standard deviation is equal to the square root of the variance, and that is equal to 1 as well. Now what is the third moment, third central moment about mu? So this third central moment about mu, it's defined as expected value of x minus mu all cubed. And that is, by definition, we calculate it as the sum over all possible values of x minus mu to the power 3 times the probability of x. Now this is equal to 0 minus 2 all cubed times 0 0.1 plus 1 minus 2 all cubed times 0 0.2 plus 2 minus 2 to the power 3 times 0 0.3 plus 3 minus 2 all cubed times 0 0.4. Alright, and now this is equal to negative 0.6. And so the next question is use the third central moment about mu to calculate skewness. And so you would say skewness of random variable x is equal to the third central moment about mu divided by sigma to the power 3. And so this is equal to negative 0.6 divided by the standard deviation to the power 3. We said here that the standard deviation is equal to 1, right? So now we can substitute it into our equation. Skewness is equal to negative 0.6 divided by 1, and so it's equal to negative 0.6. And so we said that if skewness it's less than 0, then it means that your probability distribution is negatively skewed. So it's negatively skewed or skewed to the left. And so it means that if you draw a curve over your line graph, it will look like that. So if you draw a curve over the possible values of your line graph, it will look like that. All right.